In this video, we are going to be starting Chapter 13 in your textbook by Surway and Jewett on universal gravitation. This corresponds to sections 1 and 3. Newton's law of universal gravitation says that all objects in the universe exert an attractive gravitational force on all other objects in the universe. So right now, you are exerting a gravitational force on the objects around you, and they are exerting a gravitational force on you. The force that you're exerting on an object is exactly equal to the force that it exerts on you. This is the formula for Newton's law of universal gravitation. G stands for the universal gravitation constant. M1 is the mass of object 1. M2 is the mass of object 2. And R is the distance between the centers of the two objects. So G is a number that is equal to 6.673 times 10 to the negative 11th, and those are the units that just allow everything here to cancel out. This number was calculated by Henry Cavendish in 1798 using a setup that looks something like this. He had two larger masses and two smaller masses, and he was able to calculate the angle of deflection between them, and from there he was able to calculate G. Physicists call that big G. Here is a simple example problem. What is the gravitational force between the asteroid Chiron and the Sun when the distance between them is 2 times 10 to the 12th meters? So for G, we just want to plug in 6.673 times 10 to the negative 11th. I would suggest putting that into your calculator and storing it. And then M2 is the mass of the asteroid. And then M1 could be the the mass of the Sun. And then R is the distance between them. So you just plug in those numbers, make sure you're plugging it into your calculator correctly, and you get 1.5 times 10 to the 15th newtons. So as we know, the force of gravity causes acceleration, and at Earth's surface it is equal to 9.8 meters per second squared. So the force of gravity will equal ma. And we can use this to find the acceleration of an object close to Earth's surface. We already know what it is, but we're going to be confirming it using Newton's law of universal gravitation. So we're going to say that m1 is equal to the Earth's mass, m2 is equal to the mass of the object, and the distance between the two objects is the Earth's radius. That's the distance between Earth's center and the object that is on Earth's surface. So we plug in our numbers, and then these m2's will cancel out, and then you can just solve for a, and you get 9.8343 meters per second squared, which, if you round, is equal to 9.8 meters per second squared. This will work on any planet. For example, Jupiter. So m1 will equal Jupiter's mass, m2 will equal the mass of the object, and the distance between the two objects, r, will be Jupiter's radius. So again, the distance between Jupiter's center and an object on Jupiter's surface. We plug in numbers. Again, the m2's will cancel out, and we just solve for a. And we get 25.95 meters per second squared. Obviously, the acceleration due to gravity is a lot more on Jupiter because the mass is so much more. You can also find freefall acceleration at a distance from the Earth's surface. So this problem asks us to calculate the acceleration due to gravity when an object is 3,200 kilometers above Earth's surface. m1 will equal Earth's mass, and m2 will again be the mass of the object. But this time, the distance between the two objects is the radius of the Earth plus h, h being the 3,200 kilometers. So it's the distance between the center of the Earth and so that would be RE, and then where the object actually is above Earth's surface. So we just plug in numbers. Again, the m2's will cancel out. And we end up with the acceleration due to gravity being 4.36 meters per second squared. And that makes sense because the object is so much further from the center of the Earth. So for another sample problem, at what altitude above the Earth's surface would the acceleration due to gravity be 5.1 meters per second squared? So this is maybe a little bit trickier. Instead of solving for A, we would be solving for H. So we plug in numbers. Again, the m2's would cancel out. So I'm going to do a couple things here. I'm going to multiply these two together to get 3.99 times 10 to the 14th. And then I'm going to multiply both sides by this so I can get this on the numerator rather than the denominator. And then A will be equal to 5.1. So I'm going to plug in 5.1 for A. The next thing I'm going to do is divide both sides by 5.1. That way there's just less stuff on this side. It simplifies it a little bit. Next, I'm going to FOIL this out. So we end up with this. It's a lot easier to write in scientific notation. Now what I'm noticing here is that I have a number, I have an h, and then I have an h squared. So I want to put this into quadratic form. So what I did from this step to this step, I subtracted this number from both sides. And then I plugged these numbers that you see here into the quadratic program on my calculator. So the A term is going to be equal to 1. The B term is equal to this number right here. And the C term is equal to this number right here. And I ended up getting H equals 2.25 times 10 to the 6th meters. And that makes sense because it's a closer distance than the previous problem on the previous slide because the gravity is a little bit more.